Hello everyone, this is chapter 8.1, which will discuss sample spaces, events, and probability. So first off, I want to say that a set of outcomes is called a sample space and is denoted by capital S. An event is any subset of S, which usually is denoted E. So let me actually write that in red here. So usually we'll denote an event as E. Sometimes there's subscript like E1, E2, because there's multiple events that can occur. So let's just say E sub I or something like that. And that's really all I'm going to say. The book actually discusses a little bit more, but to be quite honest, that language isn't of particular interest to us. I'll just kind of discuss a little bit of what they say without writing it down. So they say that a simple outcome or simple event is just one element of S. And an event would be a simple event if it only contains one outcome. So I don't really care for that too much, but in any event, we'll actually see each of these vocabulary and how that plays in with these examples here. So let's see. Here in this example, we're asked in rolling two six-sided dice, we want to list each of the following events. So these are certain possibilities when you roll two six-sided dice. Now, of course, we know that when you roll a six-sided dice, well, each dice has an outcome of either 1 through 6, 1, 2, 3, 4, 5, or 6. So in total, you can roll lowest to 2 or highest to 12, right? Two ones is a 2, and then 2 sixes is a 12. So what I'm going to do is, instead of actually writing it down, like you may expect to see something like this. So let's say we roll a 7, you may expect to see one dice is a 3 and one dice is a 4, let's say. But I'm not going to write this, of course. This is the visualization we get, but instead, I'm going to write this as an ordered pair, 3, 4. So rolling a 3, then a 4. So that's a possibility. So here, this set, where the roll sum is 7, well, we just saw one right here, but I'm going to write it in a more systematic fashion. So let's say we roll a 1 first, then a 6. A 2 first, then the other one has to be a 5. If you roll a 3, it has to be a 4. Now rolling a 3, then a 4 is one possibility, obviously. Rolling a 4 and then a 3, believe it or not, is in another possibility. It's a different outcome. And then rolling a 5, then a 2, then will be another one. And then a 6, then a 1 would also be another outcome. So yes, as it turns out, each of these sets of this space is an ordered pair, and this set is an ordered pair, and these are called outcomes because they're the elements. So an outcome is an element of a sample space, and since an event is a subset of a sample space, then the outcomes will also be elements of the events. So these are outcomes. So that's the language we're going to use here. Okay. Now, real quick, I'm going to have to erase this drawing so we can see what the other two will be for this example. So let's take a look. So for 2, it says the roll sum is less than 4. So let's see. Can we have 1, 1? 1, 1 will be a 2. We can have 1, 2. That'll be a 3. We could also have 2, 1. That'll be a 3. So we have the roll could be a 2. The roll could be a 3. And that's it, because if the roll sum is anything greater than this, then it'll be, 4 or bigger, but we want strictly less than 4. So I'm not even going to write rolling a 3 and a 1. In fact, rolling a 3 and any other number will be bigger than 3, and if it's bigger than 3, well, then it's going to be either 4 or more, so it won't be less than 4. So this actually is the entire set. So if your roll is less than 4, then either you roll 2 1s, a 1 and a 2, or a 2 then a 1. And those are the only possibilities. If your roll sum is 12, well, there's only one element of this set actually, so there's only one outcome, and that's if you roll a 6, then a 6. So this is an example of a simple event, kind of like I phrased earlier. Oh, by the way, is it possible to have the empty set as a subset? It is, kind of like we saw in the previous sections for chapter 7, when we spoke of empty sets. So like, for instance, what if one of the questions was the roll sum is 13? Well, rolling the 13 is impossible because the highest you can roll is 12, so that would be the empty set. So we'll still use that same language there. So now we're going to talk a little bit more about what probability is and how this affects that definition. So let's take a look at that. All right, so here for probability, if every outcome of the sample space S is equally likely to occur, then we can say that the probability of an event E is P of E, so that's the notation for probability, is just the fraction, number of elements in the subset E of S, divided by the number of elements in the set S, the sample space S. And of course, N of just means number of elements, as we saw from chapter 7. And there are a few consequences here. Of course, since E contains less elements than S does because it's a subset of S, then we're dividing a smaller number by a bigger number, meaning that it's going to be a fraction that's going to be less than 1 because the numerator is smaller than the denominator. So also it's positive. So it's obviously going to be a number between 0 and 1. It's possible that it's equal to 0 or equal to 1 if the event E is either the empty set or the sample space. You could think a little bit more about why that's the case, but I think from this quality here it becomes fairly obvious. If you replace E with the empty set, since the number of elements in the empty set is 0, you get 0 over a number, which is 0. And if we replace E with S, then we get P of S is N over S divided by itself, which is 1. So you could think a little bit more about what these mean, but that's fine. Also, I want to kind of give you some language here. You don't quite need it, but anytime an event has probability 0, it is known as impossible. And anytime a event has probability 1, it's known as guaranteed, or I guess a better word would be certainty. All right, so now let's see an example. So let's see if we can figure out a probability of a particular event occurring. So in this case, I ask, what is the probability of rolling a sum of 7 when rolling 2 dice? Now, we actually saw that in the previous problem, we were able to actually calculate that event. So we saw that the event of rolling the 7, let's say that's event E, is equal to, what was it? It was, let me see, it was 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Now, of course, this is just the event itself. But what about the sample space? The sample space will be a lot harder to write out, but let me just give you this idea. So it's the ordered pair x comma y. So each element in the sample space will be of that form, where x is going to be in between 1 and 6, and so will y actually. So this is what each outcome in the sample space looks like. Now, with that being said, can we calculate the number of these things? We definitely can. Because here, how many choices do we have for x? We have 6 choices, because it could be 1 through 6. Y can also be 1 through 6. There can be repeats, and order matters. So with that being said, the number of choices we have for this pair is 6 times 6. Think of the slot method. So with that being said, the number of elements in the sample space is actually 6 times 6, which is 36. And here we can just count. Let's see, the number of elements in the event E is, let's see, 1, 2, 3, 4, 5, 6. So it's 6. Perfect. So now what does that mean? I have a little bit of space here, so let's see. It means, now we can say, the probability of S is just the number of things, probability of E I meant to say, is equal to the number of things in E divided by the number of things in S. We know what each of these are. The numerator, of course, is 6. The denominator is 36. So this reduces to 1 over 6. So that's our answer here, 1/6. Now, of course, if you want to write this as a decimal, it's 0.1666. And if you wanted to write that in percentage, it would be 16.666%. So I guess I can write that here. So you can approximate it in decimal as 0.166 The bar on top, of course, just means it goes on and on. And then if you want to write that in percent, that's 16.66%. And in fact, if you were to actually evaluate the event of rolling any number, you'll find out that in rolling 2 dice, 7 is the one that occurs more often. So anytime you think of lucky 7, it's just because 7 has more likelihood of occurring than any other number when it comes to rolling 2 dice. Alright, so now for this example, we're going to be finding the probability of these particular events. And as it turns out, these examples will get harder and harder as we go down the list. But let's just start with the first one at the very top. So here we say 3 coins are being tossed. What is the probability that, well, 2 heads face up? So let's just say that the sample space here, sample space here will be the set of possible heads or tail tosses of a coin. So one possibility is heads, then heads, then heads. It's an ordered pair because you have, 3 possibilities, 1 for each coin. So this outcome here is the outcome of getting all 3 heads. This would be, let's say, HHT, so 2 heads first, then a tails. And then you can do HTH, let's say. And let me just write ... because I'm not going to write all of them. But I'll tell you right now that the number of elements here in the sample space, the number of outcomes, is actually 8. Which I think is fair to see because since each element is a ordered triple, there are 3 choices for that one element for each of these. Each has 2 possibilities. Either it's a heads or it's a tails. So remember, these represent the different coin tosses. The first coin toss, second coin toss, and 3 coin toss for one outcome. Meaning, for each ordered triple, it's going to be, kind of like we saw with the previous example for the sample space of rolling 2 dice. By the slot method that we saw, it's, it was 6 times 6. Here it's going to be 2 times 2 times 2. So notice that's 8. So it's a total of 8 different outcomes. I'm not going to write all of them, but if you want on your own, you can write all of them and see that there indeed are 8 of them. Now, let me write E. E is the possibility, E is the event where each of the outcomes contained exactly 2 H's. So let's see if we can do that. So here's how I'm going to do this. Either there's an H here and an H here, or there can be an H there and an H there, or I guess there can be an H there and an H there. Is that it? I think that's it. Basically what we have is we have 3 different slots for H, and we're selecting 2, so we want 2 of them to be H out of the 3. So basically we're asking ourselves, how many ways can we select 2 of 3 things? So this is just 3 choose 2, which if we recall from 7.4, 3 choose 2 is 3. So in fact this is all of them. So this is this tells us that the number of elements in E is 3. So in total, now we can say exactly that the probability of E is just the number of things in E divided by the number of things in S, which is 3/8. Nice. So it's 3/8 probability. If you want to write that in decimal, you'll get 3.7, 37.5%. But I'm just going to write it as a fraction. Right now, for the next example here, what is the probability of drawing 5 face cards from a standard 52 card deck? Now, like I said, the difficulty here increases with each example as we move downward. Now, we need to first understand the structure of a 52 card deck. Now, I don't want to talk about it too much, but I'll give you a little diagram here and then I'll erase it shortly. But I'm going to create a grid. It's not very evenly spaced, but that's fine. And the grid here will represent all of the cards. So there is an ace, 2, 3, 4, all the way to 10. And then there are 3 face cards. There's the J, the Jack, the Queen, Q, and the King, K. Now, well, the reason why there are 4 rows here is because there are 4 different suits. So the suits are, there's spades, there's clubs, there's hearts, and there's diamond. So if you look up a diagram of a 52 standard 52 card deck, you'll see what I mean. If you're familiar with how these decks work already, then you'll know that there are 3 face cards, Jack, Queen, and King. We're not taking ace to be a face card because it doesn't have a face. Jack, Queen, and King are represented by people which have faces. So that's what I'm using. Now, of course, there's 3 for each suit, so in total there are 12. So what's the probability of drawing 5 face cards? Well, since there are a total of 12 face cards, how many ways can we choose 5 of the 12? So here, I'm not going to write actually out E, but I'm going to say that the number of elements in E is just choosing 5 from 12 objects. So 12 choose 5. Similarly, for the sample space, so for the number of things in the sample space S, well, what are we doing here? We're drawing 5 cards from a 52 card deck. So we're drawing 5 cards and we want to know the probability that all 5 of them are face cards. So specifically, that's what the question says. So maybe the wording's a little off, but that's the setup here. We're drawing 5 cards and we want to know the probability that all 5 of them are face cards. So the sample space would be all possible combinations of drawing 5 from all 52 cards. That's a lot. I'm not going. I didn't even dare writing E. I'm not gonna, of course, dare to even write S. It's way too much. But let me just describe it as this. That's choosing 5 from 52 things. There we go. So now I can write out what these numbers are, if you want. They're going to be pretty large numbers. And then from here, we can find the probability of E just by dividing these numbers. Now, the biggest thing here was how we calculated them using the choose function that we saw from 7.4. So that's what makes this one difficult, as well as understanding the structure of a 52 card deck. So I'm going to compute these in the calculator and erase this diagram, and then we'll actually find out what the probability is. All right, so using my calculator, I got these 2 values. So the event E has 792 elements. So of course, no way I would write it out list by list because there's a lot of elements here. And like I was saying, choosing 5 cards from 52, there's a ton of different ways you can do that. There's about 2.5 million ways of doing that. Crazy. And if you divide these, you'll get that the probability of E then is just, well, 792 over 2598960. And that, if you approximate this, in the calculator I got 3.047, yeah, so just making sure, 47, and it gives me this funny E -4. So if you're not familiar with that, that basically is the calculator's way of describing scientific notation. So this means times 10 to the -4. So really we move the decimal place over to the left 4 times. So if you move this over to the left 4 times, 1, 2, 3, 4, we get a space of 3 after jumping over the number 3. So we get 0.0003. So this is actually about approximately 0.0003047. Which is very small. So yeah, it's very unlikely that this will actually happen. So if you shuffle a 52 card deck, if you have one laying around, and you draw 5 cards, and if they're all 5 of them are faces, then you're extremely lucky, basically. Okay, onward to the next example. So let's see how difficult this one gets. So here we have a jar. The jar contains 3 red, 2 blue, and 4 green marbles. Okay. What is the probability of selecting one of each color if you pick 3 at random? So we're reaching into the jar, we pick 3 marbles, and we have 1 red, 1 blue, and 1 green, exactly. Well, here's what we're going to do. So I'm going to say this. So again, I'm not going to actually write out the sample space or the event themselves, but what I will do is I will calculate the number of them. just trying to see how I could do this. So how many ways can we choose? So what event E is? Event E is this. It's selecting one of each color. So how many ways can you select one of each color? So let's see here. So we want to choose one red. So we're choosing one from 3 reds. And so multiply that to choosing one of 2 blues and choosing one of 4 greens. So I'm multiplying these quantities here, and basically this is the multiplication principle of counting, if you remember. So there are 3 tasks here, so we multiply the amount of ways we can do that for each task. So how many ways can you choose one of 3 marbles? This. How many ways can you choose one of 2 marbles? That's 1 choose 2. Similarly, for choosing one of 4 green marbles, that's 4 choose 1. Okay, good. But now, what is the sample space? Well, the sample space represents all possible 3 picks of marbles. So it could be green, 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 blue, red, red, blue, red, green, blue. That would be in E, coincidentally. But yeah, it's an ordered triple of that form. And the order kind of matters. Notice you can't have all of them blue because, well, there's only 2 blue. So in fact, here's what I'm going to say here. Well, how many total colors are there? Or how many total, well, there are 3 colors, but how many total marbles are there? There's 3 plus 2 plus 4, that's 5 plus 4, so there's 9 total. So you have 9 marbles in this jar, so it's not really that many. And we're picking 3 of them. So how many possible ways can you pick 3 of 9 things? So we're choosing 3 of 9, so that's 9 choose 3. So yeah, this was a little more difficult than the previous one because for the top here, for the amount of elements in E, in the event E, we had to multiply these, and it wasn't a very obvious application of the multiplication principle from 7.3, I guess. So let's calculate this with the calculator, and then we'll compute the probability. So of course I used my calculator, but after doing it I kind of realized that we could have done this by hand. Remember that we recalled from 7.4 that any number choose 1 is just that number itself. So this is 3 times 2 times 4, which is 6 times 4, which of course is 24. This we could have also used that equation we had for the formula we had for choose. I guess I could write it off to the side here. We have a little bit of space. So what would 9 choose 3 be? 9 choose 3, okay, just making sure it comes out, would be 9 factorial over 3 times, well, 3 factorial, times 9 minus 3, which is 6 factorial. Now remember that in the top, 9 factorial is 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1, but 6 through 1 is just 6 factorial. 3 factorial is 3 times 2 times 1, so we don't need to write the 1. And notice the 6 factorials cancel, right? So far so good. 2 goes into 8 4 times, and 3 goes into 9 3 times. So all we're left with is really 3 times 4 times 7, which is 12 times 7, which is 84. Good, so we can actually do this by hand. And then finally, from here, we get that the probability of E is then just what? It's just the amount of elements in E divided by the amount of elements in the sample space S. So that's 24 over 84. And you can divide each top and bottom by 12, and you will get, well, I guess, 2 over 7. Which I'm going to leave as a fraction, but you could write it as a decimal. It'd be about 28%. So it's not super unlikely this will happen. It's almost like 1/4. It's a little more than 1/4. So you have greater than 25% chance of that occurring. So that was nice. So I only gave, well, these examples after the dice example we saw. So in fact, you'll see that a lot of examples when it comes to probability will involve these type of games, which will remind you a lot of, well, gambling. Tossing a coin, rolling dice, drawing cards, picking marbles from a jar. These are all things that come to mind when you consider like games you see in that you can gamble with. And that's a big application of probability. And one thing that comes to mind is an odds of a bet and stuff like that. We'll be taking a look at ideas like this and more in the rest of chapter 8. So I'll see you in the next videos for 8.2, 8.3, and 8.4. See you then. Thanks for watching.